Dr. Anthony Raj. He has pursued his bachelor's, master's and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Thiruvalluvar Arts and Science College and Idea Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to UGC lecture series, BSc Physics Honors, Mathematical Physics 2, Semester 2, Lecture 7. In this lecture, we are going to see second order homogeneous equations with constant coefficients. First, introduction about the second order homogeneous equations, then general solution of this second order homogeneous equation, then Wronskian of this general solution, finally summary. These are all the topics we are going to see in this lecture. Introduction. The equation of the form P0 d square y by dx square plus P1 dy by dx plus P2 y is equal to 0 is a second order homogeneous equation. In this equation, this P0, P1 and P2 are all constants. This equation, the right hand side of the equation is 0. So, this is a homogeneous linear differential equation, and order of this equation is 2, because the highest derivative in this equation is second order derivative. So, that this equation is second order homogeneous linear differential equations with constant coefficients. This homogeneous equation is obtained from linear differential equation of the form P0 d power n y by d x power n plus P1 d power n minus 1 y by d x power n minus 1 plus P2 d power n minus 2 y by d x power n minus 2 plus etc. plus P n minus 1 dy by dx plus P n y is equal to q. So, this is a homogeneous equation. From this equation, above second order linear homogeneous equation is obtained. In this equation, this P0, P1 and P2, Pn minus 1, Pn q are all functions of x or constants. These P0, P1, P2 are all functions of x or constant. Then this P0 should not be equal to 0, that is the condition for this homogeneous linear differential equation. Now, let us come to the general solution and Wronskian of this homogeneous second order differential equation. To determine the general solution of homogeneous linear differential equation, first we must find two linearly independent functions that satisfy it. Once these solutions are found, the general solution is given by a linear superposition of the functions. So, first we need to find two linearly independent functions that satisfy it. Once these linearly independent functions are obtained, the general solution is given by a linear superposition of these functions. Suppose if the two functions of P0 d square y by dx square plus P1 dy by dx plus P2 y is equal to 0, where P0, P1 and P2 are constants are y1 of x and y2 of x. Suppose this y1 of x and y2 of x are the two solutions of this second order linear homogeneous equation, then the general solution is given by yc of x is equal to c1 y1 of x plus c2 y2 of x, where this c1 and c2 are arbitrary constant. So, we assumed two functions y1 of x and y2 of x. These two functions are manipulated as a linear combination. That linear combination is given as yc of x is equal to c1 y1 of x plus c2 y2 of x. The linear combination of this yc of x is called complementary function. So, this complementary function is the solution of the second order homogeneous linear differential equation. Now, if y is equal to r of x is a particular integral of the equation 1, the general solution is given as y is equal to c1 y1 of x plus c2 y2 of x plus r of x. Thus, the general solution of a homogeneous equation consists of the sum of the complementary function and a particular integral. This is a solution of a second order homogeneous linear differential equations can be theoretically studied. Now, linearly dependent and independent solution. So, in the earlier part we learnt how the solution of a homogeneous differential equation exists. Now, the dependent and independent of the solution, linear dependency and independency of the solution obtained. For that, again consider a second order linear differential equations with constant coefficient. This is the form of second order linear differential equation with constant coefficient. In this equation, this p0 y double prime of x plus p1 y prime of x plus p2 y of x is equal to 0. This is the considered second order linear differential equation with constant coefficient. Then the two solutions for this equation is y1 of x and y2 of x are said to be linearly dependent if there exist two constants c1 and c2, not both 0, such that c1 y1 of x plus c2 y2 of x is equal to 0. So, then only these two solutions, that is y1 of x and y2 of x are said to be linearly dependent. Now, if the two solutions y1 of x and y2 of x are said to be linearly independent, if c1 y1 of x plus c2 y2 of x is equal to 0, where c1 is equal to 0, c2 is also equal to 0. So, this is the condition for the non-dependent, linearly non-dependent of the two solutions of the homogeneous equation. The two solutions are y1 of x and y2 of x. So, from this part we learnt that the linear dependency of the two solutions, the condition for the linear dependency of the two solutions are c1 y1 of x plus c2 y2 of x is equal to 0, such that the constant c1 and c2 not both 0. Now, linear independent, for linear independency, that c1 y1 of x plus c2 y2 of x is equal to 0, where c1 is equal to 0, c2 is equal to 0. But for the case of linear dependency, this c1 and c2 both should not be equal to 0. For independent, that c1 must be equal to 0, c2 must be equal to 0. This is how the linear independent and linear dependency of the solutions of second order homogeneous linear differential equation can be learnt. Now, the Wronskian, the definition of Wronskian. Let y1 of x and y2 of x be two solutions of the second order differential equation. the second order differential equation is P0 y double prime of x plus P1 y prime of x plus P2 y of x is equal to 0. This is the assumed second order differential equation. Then for this second order differential equation, this y1 of x and y2 of x are the two solutions. Then the Wronskian is denoted and defined as the determinant w of y1 y2 or w of x is equal to determinant of y1 of x y2 of x y1 prime of x y2 prime of x. This is how the Wronskian of the solutions are determined. Some important theorem on solution. So, these theorems are based on the Wronskians of the solution. Theorem 1. If y1 of x and y2 of x are any two solutions of the second order differential equation P0 y double prime of x plus P1 y prime of x plus P2 y of x is equal to 0, then the linear combination of C1 y1 of x plus C2 y2 of x, where C1 and C2 are constant, is also the solution of the given equation. So, this is the first theorem regarding the solutions of second order homogeneous linear differential equation. So, from this theorem what we learnt is if y1 of x and y2 of x are any two solution, then linear combination of these two solution is also a solution. That is what this theorem says. Now, let us go to the next theorem, Theorem 2. If there exists two linearly independent solution, we know the condition for linearly independence of solution. The condition is C1 y1 of x plus C2 y2 of x is equal to 0, where C1 is equal to 0 and C2 is equal to 0. That is the condition for linearly independent of the solution. So, the second theorem is about the linearly independent solution. So, the theorem states that if there exists two linearly independent solution of y1 of x and y2 of x for a second order linear differential equation, then every solution y of x may be written as y of x is equal to C1 y1 of x plus C2 y2 of x, where this C1 and C2 are suitable chosen constant. This is the second theorem about solutions. So, the second theorem says that if there exists two linearly independent solution, then every solution y of x may be written as the linear combination of that two linearly independent solution. This is the second theorem. First theorem is about the linear combination of solution. If y1 of x and y2 of x are any two solutions of a second order differential equation, then linear combination is also a solution. That is what this first theorem says. The second theorem is about the linearly independent part of the solution. If there exists two linearly independent solution, then every solution must be written as, may be written as the linear combination of that linearly independent solution, where C1 and C2 are arbitrary constant. Now, Theorem 2 about solution. Again, two solutions y1 of x and y2 of x of the second order equation are linearly dependent if and only if their Wronskian is identically 0. That is, y1 of x into y2 prime of x minus y1 prime of x into y2 of x is equal to 0. This is the value of the determinant. The value of the determinant must be equal to 0 for the two solutions y1 of x and y2 of x are linearly dependent. So, this is the theorem about solutions of second order linear differential equation. Corollary to this Theorem 3, it says that two solution y1 of x and y2 of x of the equation are linearly independent if and only if their Onskian is not 0 at some point x naught where this x naught belongs to the interval a comma b, where the x naught belongs to the interval a comma b. So, theorem 3 talks about the linearly dependent of two solutions. For the linear dependence of two solutions, the value of that Onskian must be 0. In the corollary to theorem 3, two solutions of the equation are linearly independent if and only if their Onskian is not equal to 0 at some point x naught, where that x naught should lie in the interval a and b. Next, theorem 4. The Onskian of two solutions of the equation a naught of x y double prime plus a 1 of x y prime plus a 2 of x y is equal to 0, where a naught of x, x belongs to a comma b, is either identically 0 or never 0 on the interval a comma b. So, this is the theorem 4. This theorem 4 talks about the Onskian of two solutions, Onskian of two solutions. This Onskian of two solutions is either identically 0 or never 0 on the interval a comma b. These are all the theorems about solutions of the homogeneous linear differential equation. Now, we will do a problem about these solutions. So far, we have learnt the solutions of a homogeneous linear differential equation. We learnt that Onskian of a solution, that is how to determine the Onskian of a solution. In this example, you are asked to prove that sin 2x and cos 2x are solutions of the differential equation y double prime plus 4y is equal to 0, and these solutions are linearly independent. This is what we need to prove in this problem. Solution to this problem may be started like this. The given equation is y double prime plus 4y is equal to 0 is the given equation, and the given solutions are sin 2x and cos 2x. Let us assume y1 of x as sin 2x and y2 of x as cos 2x. These are the two solutions given. What we need to do is, we have to prove the two solutions of the differential equation are the linearly independent. That is what we need to prove. So, first find the first derivative of this sin 2x, that is first derivative of y1 of x, that is y1 prime of x is the first derivative, which gives 2 cos 2x. Then first derivative of this y2 of x. First derivative of this y2 of x is said as y2 prime of x is equal to minus 2 sin 2x. This is the y2 prime of x. Then find y1 double prime of x. That y1 double prime of x is equal to minus 4 sin 2x, minus 4 sin 2x. Now, substitute this y1 prime of x and y1 double prime of x in the given equation. So, the equation will change as y1 double prime of x plus 4 y1 of x, which is equal to minus 4 sin 2x plus 4 sin 2x. So, minus 4 sin 2x plus 4 sin 2x, which is equal to 0. Hence, that y1 of x, which is assumed as sin 2x, is a solution, of the given differential equation. So, to prove the given solution as a solution, we need to substitute the solution in the given equation. If that equation is satisfied, then the assumed function is a solution. Similarly, we can prove that y2 of x is a solution of 1. We know the value of y2 prime of x and y2 double prime of x. y2 double prime of x is equal to minus 2 into 2 cos 2x, which is equal to minus 4 cos 2x. Now, substitute this in the equation. So, the equation can be written as y2 double prime of x plus 4 y2 of x. Now, substitute the value y2 double prime of x. y2 double prime of x is minus 4 cos 2x. So, minus 4 cos 2x plus 4 y2 of x is what? This is y2 of x, cos 2x. So, cos 2x, again these two will get cancelled, you will get 0. Hence, this y2 of x, which is assumed as cos 2x, is also a solution, This is how we can prove whether the assumed function is a solution or not of a given differential equation. But in the problem, it is asked that and these solutions are linearly independent. First, we have proved the sin 2x and cos 2x are solutions of the given differential equation. The next part of this problem is we need to prove these solutions are linearly independent. To prove that linear independency, we need to go for the Wronskian of the solution. The Wronskian of the solution is written as w of x is equal to determinant of y1 of x, y2 of x, then y1 prime of x and y2 prime of x. This is the Wronskian of the given solutions. Substitute the solution and its solutions and its derivative. So, this determinant will change to sin 2x cos 2x, then y1 prime of x is 2 cos 2x, y2 prime of x is minus 2 sin 2x. If we expand this determinant, we will get minus 2 sin square 2x minus 2 cos square 2x. Now, take minus 2 as common from this part. So, the equation will change as sin square 2x plus cos square 2x. This is in the form of sin square theta plus cos square theta. According to trigonometry, this sin square theta plus cos square theta is equal to 1. So, we get minus 2. This minus 2 is not equal to 0, So, Wronskian of the solutions w of x is not equal to 0. Therefore, that sin 2x and cos 2x are linearly independent solutions. Therefore, that sin 2x and cos 2x are linearly independent solutions. Of the given differential equation. This is how we can check whether the given solutions are linearly independent or not. So, from this problem we learnt how to check whether the given function is solution of the given differential equation or not, and how these solutions are linearly independent or not. These are the things we learned from this problem. Next we will do one more example. In this example we will see that the solutions are linearly independent, so that the constant C1 and C2 can be determined. So, the exact thing of this problem is show that y1 of x is equal to sin x and y2 of x is equal to sin x minus cos x are linearly independent solutions of the differential equation y double prime plus y is equal to 0, and determine the constant C1 and C2, so that the solutions sin x plus 3 cos x is equal to C1 y1 of x plus C2 y2 of x. This is the problem. Solution to that problem will be like this. Given equation is y double prime plus y is equal to 0. Here y1 of x is sin x, then y1 prime of x, that is first derivative of that y1 of x is equal to cos x, then second derivative of this y1 of x, that is y1 double prime of x is equal to minus sin x. Substitute these values in the given differential equation. So, the differential equation will be y1 double prime of x plus y1 of x is equal to minus sin x plus sin x, which is equal to 0. So, that y1 of x is a solution of the equation 1. Similarly, we can show that y2 of x is also similarly y2 of x is also a solution of the given differential equation, solution of the given ordinary differential equation. Now, the Wronskians of this solution, w of x is equal to y1 of x into y2 of x, y1 prime of x and y2 prime of x. Determinant of these solutions and its derivative gives the Wronskians of this solution, which is equal to sin x minus cos x, then cos x, then cos x plus sin x. So, if you expand this determinant, we will get sin x into cos x plus sin x minus cos x into sin x minus cos x. If you expand this, you will get a value equal to 1, which is not equal to 0. So, the solutions y1 of x and y2 of x are linearly independent solution of the given differential equation. Linearly independent solutions of the given differential equation. Therefore, sin x plus 3 cos x is equal to C1 y1 of x plus C2 y2 of x, or if you simplify this, you will get sin x plus 3 sin x plus 3 cos x is equal to C1 sin x plus C2 the y2 of x. y2 of x is sin x minus cos x. Sin x minus cos x. Comparing the coefficients of that sin x and cos x, comparing the coefficients of the sin x and cos x, we get C1 plus C2 is equal to 1 and C2 is equal to 3. So, that the value of C1 is equal to 4 and C2 is equal to -3. So, this is how the values of C1 and C2 can be obtained from this equation. So, from this equation what we learnt is how to check the linearly independent solutions, how to check whether the given solutions are linearly independent or not, and using that concept how to determine the constants C1 and C2 of the given differential equations. So, in this lecture we learnt that the equation of the form P naught d square y by dx square plus P1 dy by dx plus P2 y is equal to 0 is called the second order homogeneous differential equation. The general solution of a homogeneous differential equation will be of this form: y is equal to C1 y1 of x plus C2 y2 of x plus r of x. So, this is the concept we learnt from this lecture. So, the general solution consists of the complementary function and a particular integral. The Wronskian is denoted and defined as w of y1 y2 or w of x is equal to determinant of y1 of x, y2 of x, y1 prime of x, y2 prime of x. This is how the Wronskian of solution are defined. So, after listening to this lecture you can answer following questions, that is if y1 of x is equal to sin x and y2 of x is equal to cos 3x are two solutions of differential equations y double prime plus 9y is equal to 0, show that y1 of x and y2 of x are linearly independent solution. Define Wronskian of solutions. Then state any two important theorem about solutions. So, you can answer these three questions after listening to this lecture. Thank you.